guys are ready. This is what I worked on for my thesis research, using DNA for data storage, mostly algorithm development for encoding and decoding. And it's a relatively newish area of research. I think in the last 10, 15 years, it's gotten a lot of, gotten more recognition and more research. But yeah, hope you think it's interesting. And Kelsey again. I'm on LinkedIn if anyone wants to touch base or any other questions. So jumping right into some of the background and motivation for this kind of project. We've all heard terms like big data and explosion of data, but I think it's also interesting to look at how we've gotten to this point with the growth of digital data. So a couple bullet points on the timeline here. When I was doing some of the background research, I found this quote from a guy in 1997 who, at the time, he was trying to figure out how much digital data there was in the world at that time. And he's recorded as saying, storage media will outrun our ability to create things to put on them. So just one example of someone who didn't foresee, this doesn't speak for everyone, but maybe they didn't really see just how much data we would have. And then fast forward to 2013, 90% of the world's data had been generated in just the previous 2 years. So we're starting to see that growth. And now by 2040, analysts estimate that the global memory demand could potentially exceed the supply of silicon by 2040. So kind of interesting, that provides a little bit of motivation. Researchers are looking into different types of data storage, and this is just one of them using DNA. So, a couple advantages of why researchers think this is a viable option. The biggest one is information density, just the size of DNA itself. Potentially 1,000 times greater information density than flash memory. And then second, retention times could potentially range from hundreds to thousands of years. So one application is definitely cold storage at this point. And then the energy efficiency could be up to 100 million times more efficient for the operation. There are disadvantages though as well. A couple of things that we're working on and researching. Read-write times are pretty slow for just physically creating the DNA and reading that back. The cost is expected to drop, but at this point it could be thousands of dollars for megabytes, even just a 1 megabyte file. And then high error rates, depends on the technology that you're using, but it could be up to 10% per base. So a couple things to consider. The overall process of how this system works is basically starting over here on the left, we've got our binary or digital data, and that gets put through an encoding algorithm to give us our sequences of nucleotides here. Those are the 4 molecules or bases that make up DNA, A, T, C, and G. With those, that goes through the DNA synthesis technique to create the single-stranded DNA, which can be then stored in a test tube for however long it's needed. And then when we're ready to read back that information, the DNA goes through the sequencing process. After that, we'll get those sequences back again, and then that can be put through the decoding algorithm to hopefully give us our original data back. So the right-hand side of this diagram here is mostly for the biologists and material scientists that are working on that. We've got some people in the other departments at Boise State that are doing that kind of research. So the focus of my research was this left-hand side here, the encoding and decoding algorithm, and writing programs to do that. To start off, as a very basic approach, you might think of something like this mapping scheme over here on the right. Just one bit, 0 to A or T, 1 to C or G, and then up to 2 bits as well. You can do that, but there are also a couple of things that we need to add and a couple things to think about when coming up with the overall algorithm. So the first thing is a scalable addressing technique. The DNA strands themselves will be pooled together in a test tube, and we need some way to put those back in order to be able to piece our information back together. And we want it to be scalable too, to reach the demands of industry for storing a lot of data. The second is some sort of parity information, such as redundancy or an error correction code. So that's important because the synthesis and sequencing techniques at this point aren't 100% accurate. So there are errors that could be introduced into your data, and we want to be able to fully recover the information in case anything happens. So with those two requirements, we also want to consider the information density. Just as a quick visualization of that, a little example, if you think of this as maybe a DNA strand, and each box represents a nucleotide or base, then the blue could be the address, and that reddish color over there is maybe the error correction, but there's a certain amount of space in each strand that's allocated for those, and if you give those too much space, that would cut down on like the middle part, which would represent the actual data. So we're looking for a high information density and the ability to store a lot of data, so we want to balance out all those things. Last thing to consider here is certain patterns that we want to avoid in the final strands or sequences. So these patterns come in the form of maybe repetitions in which the molecules of the DNA want to bond with each other, and that could cause kinks or issues in the strands that make it difficult for those synthesis and sequencing processes. And those errors can be seen in the form of insertion, deletion, or mutation errors on a nucleotide basis. So we want to try and avoid those certain patterns, but again, there are errors that can still happen, so we want to recover those. Our approach for solving this problem is we first started with this mapping scheme, and our idea was to convert hexadecimal to codons, or sequences of 3 nucleotides. We excluded certain codons from our mapping scheme, which are listed up here. We wanted to avoid those repeating nucleotides, and then the other codons in there are known as start codons, which would signal something to start decoding or translating the DNA. So we left those out in the case that our synthetic DNA comes into contact with some sort of organic material. We don't know what could happen, but it also shows that we can exclude certain sequences. And then along with that, we want to consider 2 codons next to each other, one after each other. We also don't want to see those sequences in the overlap. Because of that, there were a few other codons that we couldn't have in the mapping itself, because they would likely lead to those that we wanted to avoid. So that left us with 39 codons in that table. And then once we had the mapping done for the overall encoding and decoding of the algorithm, we used something called fountain codes. And originally this was used for sending information over communication channels where there might be noise in the channel, where you could lose information or your information could become corrupt. And I don't want to go into too much detail about how this algorithm works, but kind of high level is your original file or data set here gets broken down during the encoding into packets that are otherwise known as droplets, going along with the fountain codes. But each droplet here includes some portion of your information. So the file or whatever is broken up into pieces, and then each droplet gets some piece, and then you can have overlap in your droplets that might have overlapping information. That way, when the packets get sent over the channel, if you lose any, then on the decoding side, we're going to collect all those droplets, and if one is lost or corrupt, then that information can be found in one of the other droplets. And then once enough droplets are collected, you piece together your information and you get your original data. Oh, and then the last part of this for using this algorithm for DNA data storage is this last part here. Once we have our binary and our droplets, that gets converted to the DNA sequences using the mapping that I talked about in the last slide. And then when we're ready to decode our DNA, it goes through the reverse of the mapping and then through the decoding of the fountain codes. So that was our approach for encoding and decoding algorithm and the whole system. Unfortunately, we didn't have the ability to do lab tests. That's for future. Hopefully we'll get to do that. Instead, I just created some simulations to kind of test and see how well this would work. Basically, I randomly created some data, put that through the encoding, and then added insertion, deletion, and mutation errors to that, and then put it through the decoding to try and recover the original information. So the redundancy comes in the amount of extra droplets that are created in the fountain codes. And we're getting around 95 to 99% depending on the file size and the amount of redundancy. So that was the sliver of research that I worked on, but I think there's also a lot of potential in this area for more things, more projects to work on and more research. I was just kind of brainstorming a couple examples. One idea is kind of along the lines of information theory and how much information you have in a given sequence. And then given that sequence, what's the probability that it might have errors, or what kind of errors can you find? And also for just one sequence, if you've seen a certain set of nucleotides, what's the probability or what's the chance that you'll see other nucleotides come after that, following some of those constraints that I mentioned. Clustering sequences is something that people have researched for this error correction along those same lines. If you have similar sequences, maybe you can find those errors. And then for the mapping as well, there's potential for more research there. one idea is to kind of look in nature and see if there are certain sequences that are more common, use that to direct the mapping, and then potentially you could maybe use AI search type algorithms to find an optimal mapping scheme that you could use. So just a couple things to think about. That's pretty much all I have. So if there are any questions or anything you want to go back over.
So the error rate you listed in incorrect or correct, that was without error correction?
That was with the error
That was
correction.
with, okay.
Yeah. So there's still a few errors that we weren't able to recover.
So with the parity, right?
Yes.
Yeah, parity. So how many parity bits?
So the 10%, 15% that I had up there is overall file size.
So is it just me, or did the larger 1 to 2 megabyte file have a significantly less error rate, even though it had the same redundancy as the smaller files?
Yes.
That's super weird, right? Because isn't there more room for error? Or what is it?
Yeah, it's in how the fountain codes algorithm works. So I didn't go into the details on that, but it uses a certain distribution and random number generators that's seeded. So on each side you can get those values. And for the smaller files, I think it's more difficult to hit that distribution accurately.
Okay.
So, yeah.
All right.
Yeah.
Hey, I really appreciate the pitch on the information and how you recoded it. That was really good. But I don't have any idea how this works. I'm imagining, how do they get the information to the DNA strands? What's that process? Is it chemical? Is it? I just see on TV and they have those big things squirting stuff in. How does that work?
Yeah. So I don't know the details exactly of how that works. That's not something that I researched. The best that I can add to the description is taking DNA from some bacteria or something and then using the molecules of that to basically we tell it what molecules we want to be pieced together.
Does Boise State have the equipment to do that, like in a prototype or experimental?
I think we have the equipment. The issue is cost. So it would actually be cheaper for us to send it out to another lab that specialized in that. Yeah.
I oftentimes create sequences and just send them, like you said, to a lab, and they can create them. We actually have the ability now to create chromosome size, that'd be 200-300 million bases from scratch.
Wow.
So it's not difficult.
Does the lab then keep that DNA in its container there, and then when you want to read it back,
No, it's just
or they send it to you? Do you?
right.
Yeah.
Yeah. Right. You can cost like I don't know, like 15 cents a base pair. So you can imagine in certain sizes. Going back to what you said, that's one slide you said, oh, I'm responsible for the left side.
Yeah.
The right side. There are technologies that are, I mean, it's just changing every day, really. The DNA synthesis and DNA sequencing, you probably heard of Oxford nanopores technologies. It's a new type of DNA sequencing technologies where you can read what you have up there. You're limited to only reading 200-300 base pairs, but Oxford nanopores, you're now capable of reading hundreds of thousands, if not millions of base pairs. True, the error rate is a little high, but they can get it down lower. And what makes it so unique is that with your method there's a few reaction there that adds to the error. But for their technology, there's no reaction whatsoever. They can actually read from the cell itself. So as technology advances, you may see some of this error disappear, and also you may be able to use some of those codons that you may deem unacceptable. I find it very fascinating. And so the molecular side or the wet lab side is still advancing, and you may, well, researching in your field, may have to change to accommodate that, or they may force you to change.
Yeah, maybe. And I think, I don't know all the details of this side, the synthesis and sequencing, but I think the technologies do make use of some of those computer science applications already for reading the sequences, and then if there's multiple reads, like grouping those together to give you your actual output.
Yeah, the overlapping thing you were talking about is standard procedure in DNA sequencing.
Yeah.
Right, and
They just read that, they get very short sequences of DNA, and they read thousands of them. And then basically you look for the places where they overlap.
hundreds of millions of them, really. And, but I have to say that
Huge.
the company I mentioned, it has the potential to disrupt the NGS technologies. And I'm really, how they do it's very crafty. And instead of using just fragments of them and trying to line them up, which is computation intensive, you now be able to read hundreds of, thousands of base pairs, and then lining those long sequences up is quite easy.
And if I'm remembering right, in terms of other groups that are doing this kind of research, most of them are within the NGS technologies, but I think there is one group that's using that.
The nanopores,
Yeah.
that's huge, man.
So, yeah, any other questions, comments? Yeah.
Well, in theory, could you just pull DNA out of like a bacteria or something and like read it and see if there's any meaningful information in it, encoded in it? Because that whole idea of, and I mean like unused genomes, because there's a lot that isn't utilized, why does that exist and why is that in some things? It'd be interesting to see if it actually contains information and it's kind of like a vehicle like you're talking about for data.
Yeah, and if you could some way say how that relates to like a digital data, or have some mapping to connect those, then maybe you could just use that and have it be something meaningful for us, as well as whatever other meanings it might have. So, yeah, interesting.
It's very cool what you're doing with it.
Cool. Thank you. Great.
Jesse knows how to bribe the crowd.
Start.
I did, so I'm bribing everybody. I'm distracting you. Don't fall for it. See, there you go. So these have concepts on them. And whenever you hear your concept, if you could pass it to a friend, it's okay if you have more than one, and even the same ones. And I might toss a couple out during the presentation. So this is going to be a talk on Google's cloud platform. So if you've heard of Azure, if you've heard of Amazon Web Services, and then Google, and if you've heard of Oracle and IBM, they've got like 1%, but they're out there. Hopefully you don't have to work on them. Because GCP is great, AWS is great, and Azure, they're the biggest players, in the field right now. So they're widely adopted, and you're probably going to run into them at some point or another, and you might actually have to work with more than one at the same time. So you might have, cheaper storage in AWS, but you might have all your processes, in GCP, and then you have to figure out how do I get the data over here, and it's the whole ETL problem again, all over again. And let's see if we can get this guy maximized.
You might have to use the mini screen on the desk behind
Which one?
the touch screen that's really tiny and black.
Oh, I see it over here. Which one did you use, Kelsey? What button do I press? Laptop?
Yeah.
Like every conference call that we're on, how does this work? We don't. Oh, okay, here we go. So how do I move this over so it doesn't have the notes on there? Move this guy over. Yeah, let's do that. That's not what I wanted.
I think you have to change the way the swap displays, yeah. There you go.
Perfect. Okay. So wish I had a remote. Well, I'm going to take you from 0 to GCP and discovery of the most important concepts. We're going to have an example pipeline. We're going to have a little Q&A, trying to keep it real short. I'm Juicy K, so I'm sorry, I am also Tyler Durden. So if you've seen me before, I promise we have not met unless it was in this group, but if you've seen me out somewhere else, you have met my Tyler Durden. My twin that seems to be everywhere, but everywhere that I'm not. But I am actually Jesse K. So I'm a data engineer, work with ETL, pipeline, streaming data, data modeling, SQL, disaster recovery, automation, just general solution architecture. I work with the data, right? But that was a lot of buzzwords. So what I really do is I deal with the data so the scientists don't have to. I have data skills, right? So if you've seen Office Space, and if you've worked, and spent 80% of your job, trying to get the data you're trying to analyze instead of actually analyzing, all right, you're building labels and predictions. I'm on your team, I'm trying to work with you. Not every team has a data engineer, and sometimes they don't play nice, but I try to be on your side, and I try to get you exactly what you're looking for, the way you need it to be. So we'll start 0 to GCP, and we're going to talk about some of the concepts. Specific technologies are going to be BigQuery, which is a fast, highly scalable, fully managed cloud data warehouse with built-in machine learning. What's really cool to me is that you can query a table while data is still streaming to it, and then end up reading that new streamed in data. Google actually has a lot of technologies that are really cool. But some of them are the same old. Google Cloud Storage is your same bucket storage. You just store any object you want. It's just a file system. You can grab it with Python. You can grab it, with Java, even Node.js, and Google's supporting a lot of things now. Actually, a lot of languages, and really you can develop your own and query. They're all just REST endpoints, so you can develop whatever you want to. Actually, whatever's easier. PubSub is Google's reliable, real-time, simple event stream. So if you've worked with Kafka or if you've worked with RabbitMQ, PubSub is really just a message queue. So it streams your data, it's guaranteed at least once delivery. And so you can rely on it, and it can actually, these message queues are nice because you might have 20 applications in your enterprise, but if you know how to send data to PubSub or Kafka or whatever the message queue is, and you know how to pull data back from it, that's all you need to know. You don't have to talk to 19 other applications around the enterprise. You just talk to PubSub and have it talk to you, whether it's push or pull, and that's supported. Dataflow is a simplified stream and batch data processing with equal reliability and expressiveness. That is Google's definition. What Dataflow actually is it runs on Apache Beam, and it allows you to process streaming data and batch data at the same time. Your default window for timing is a global, just single window, but if you wanted to divide up your streaming and batch data until 24 hours in a day, and some data arrived late, you have all of your calculations that have been calculated, but some data arrived 2 hours later, it puts those back into that first window by checking the timestamp, and then it recalculates what your projection actually was. And you can set an expiration as well, so if the data is too late, well, it doesn't get calculated. You can get now we're done, this is what it looks like, and we throw everything else out. Dataflow is really cool, and really it's expanding the open source Google Apache Beam project. That's really what it is under the hood. You can use Java, and you can use Python to program it mostly. So all the Python developers out there, Google really is supporting. They used to be a Java-only company until they realized that actually there's a lot more out there that people want to use. They don't want to port everything to Java. ML Engine allows you to build superior models and then deploy them into production. So you build your model out, and you can really hook it into a lot of the other GCP products. So you can subscribe to PubSub, you can pull objects, JSONs or something directly from cloud storage. You can pull things directly from BigQuery. And then Dataproc is a faster, easier, more cost-effective way to run Apache Spark and Apache Hadoop. So if you've ever built a Spark stream before, or if you've ever worked with a Hadoop cluster, if you've ever had to set one up, Dataproc makes it's literally a minute, right? And that includes sometimes 2 minutes, and that will include the stand-up of all your master nodes, all of your worker nodes, and then you can adjust them on the fly with memory or cores or whatever you need to tune your process. And then when you're done, you destroy it, because it is really actually that simple to do it programmatically, and you have a nice drop-down GUI. It makes Hadoop a lot easier than it has been circa 2014, back in 2.0 and everything. So GCP specific technologies, we've got Spanner, Bigtable, App Engine, Data Store, Cloud Functions, TensorFlow. TensorFlow is Google's, it's an open source framework and they really like using that with their ML engine. Data Store and Bigtable are some object store databases. App Engine and Cloud Functions App Engines are stateful, serverless applications or modules that end up forming an application. Cloud Functions are kind of ephemeral, just functions. They do something. If an object lands in the bucket, it reads it in and maybe puts it over here or transforms it or whatever you want it to do. And then Google Spanner is a globally and horizontally scaled, strongly consistent relational DB. Essentially, it's Google's CAP killer. So if you've heard of CAP theorem, I haven't worked with it a lot, but it's pretty cool. It spans and it's global and everything. But I really think their BigQuery combined with their Bigtable provides a lot of value much more quickly. So on to some general concepts. We have the internet and we have the cloud, and they have some similarities. They don't weigh anything. They're completely demagnetized and they're completely wireless. And both get the best reception on top of Big Ben. And it's actually an IT crowd reference, but I thought it was funny. But pay attention, so we're going to talk about some real stuff. So what is serverless and what is infrastructure as a service? So serverless is going to be your ephemeral objects and technologies. They're typically automatically scaling, so as you throw workloads at them, you don't have to think about it. It says, oh, I'm getting a lot of I/O. Well, we'll just replicate our process. It kind of load balances for you on the fly. You just create the one cloud function, and as you throw more data at it, it scales for you. And as those, of course, they're on VMs and something in the background, but you don't have to worry about that. It's infrastructure as a service. It's serverless, where all you focus on is coding and getting the load to it, and it handles everything else. Failures, scaling up, scaling back down. You don't have to put it in an auto-scaling group like on Amazon. You don't have to, do any of that. It's really, you just code it once and let it go, and you're done. Infrastructure as a service, no object management, it's self-repairing. The infrastructure layer is essentially transparent, like if you App Engine or BigQuery, once the data's in there, you don't have segments going down, you're not recovering, you're not necessarily taking backups and restores, you're not waiting for batch jobs, tables aren't necessarily locked while it's doing a vacuum or something. A lot of these things that happen when you're trying to maintain an enterprise structure and all the components in it, that goes away in the cloud. So the next general concepts are going to be ETL, extract, transform, load, and sometimes it's ELT, sometimes it's just extract and loading. And then we have streams or streaming data. And really what we're doing is we just need to take the data here and push it somewhere else. Move the data, transform the data, move and transform the data, and then streams is data in motion, whether that's real time with Spark, Storm, or Apache Beam, or it's batch with Apache Beam, or like database dumps, or just batch data that gets there, and that we're trying to move from here to there. General concepts or sources are really going to be our data sources.